Hello everyone. In this lecture I will take three numericals which will be solved using Bernoulli's principle. The first is the pipe of diameter 0.3 meter carries water at a velocity of 24.4 meters per second. At points A and B, the pressure and elevation were 361 kilonewtons per meter square and 288 kilonewtons per meter square, and elevation is 30.5 meters and 33.5 meters at A and B respectively. If the flow is steady, find the head loss between A and B. So here head loss means energy loss, because when any liquid is flowing through a pipe, it carries energy. That energy is expressed in terms of three heads according to Bernoulli's principle. Well, before we solve this numerical, let us understand different terms which are used in Bernoulli's theorem. So according to Bernoulli's theorem, the energy of liquid per unit weight of the liquid is expressed in terms of head or height, you can say, of liquid. So that means P by W plus V square by 2Z plus Z. So this is in fact energy stored in the liquid due to height of the liquid from some datum, as well as kinetic energy due to its velocity, as well as due to pressure which is there due to head differences when it is flowing in pipe. So if we multiply this equation with weight of the liquid, then what will we get? In this first term, P is pressure, which can be written as Newton per meter square, divided by W, which is specific weight, which should be weight per unit volume, Newton per meter cube. If I multiply this with weight, which is expressed in terms of newtons, what will I get here? Newton meter, which is work done, like energy, it is joule. Similarly, if I take this V square by 2Z and multiply this with weight of liquid, again I will get the same thing, that is energy. So velocity is meter square per second square upon 2Z. G is acceleration due to gravity, which is meter per second square, into weight is newtons. So here also if I solve, I will again get Newton meter as the term, as a unit. So that is again joule. And if I multiply Z, the last term, with weight W, I'll get again Newton meter, because Z is height of the point in the pipe from some datum, from some reference. So that is in meters, this is in newtons, so I'll again get Newton meter, which is joule. So this is in fact energy carried by liquid per unit weight. So whenever we multiply some weight of the liquid, we'll get the total energy being carried by that liquid at any given section. Now let us solve this numerical. At point A, we are given pressure, which is equal to 361 into 10 power 3 Newton per meter square. So this was 361 kilonewtons per meter square. So I have converted that into newtons per meter square, divided by W. W will take as 9810 newtons per meter cube, because for water we know specific weight, which is gamma or W, that is 1000 kilogram force per meter cube. So in terms of newtons, it will be simply 9.81 into 1000. So that is 9810 newtons per meter cube. So I get P by W, that is pressure head at A, as 36.8 meters of water. Then get V square by 2Z, which is called as kinetic head or velocity head, and that will be V, which is given to us as 24.4 meters squared. 2G is 9.81 meter per second square. So we get it as 30.34 meter of water. So this much of height of water is equivalent to this energy. And Z, which is datum head, which is nothing but elevation, that is given as 30.5 meters in the example. So here we have Z, P, and velocity is same. So this is V, and this is head at A, this is head at B, ZB, this pressure is at B, and this is pressure at A. So we have all the data with us. So we get these at heads of water at point A. Now at point B, get these values P by W. So this time we have 288 into 10 power 3 newtons per meter square upon 9810 Newton per meter cube. So we get it as 29.36 meters. And velocity head at B will be equal to v square by 2g, that is 24.4 square upon 2g. So this will be 30.34 meter. It is same as at point A because velocity is constant. Now let us see what is ZB, that is datum head. It is given as 33.5 meters in the question. Now calculate the total head at A and at B. So at A it is sum of all the three heads, that is 36.8, 30.34 and 30.5. Just take the total of these three values, 36.8 plus 30.34 plus 30.5, so we get it as 97.64 meters. And at B we have sum of these three values, 29.36 plus 30.34 plus 33.5, so this becomes 93.2 meters. So it can be easily observed that there is a drop in head when water flows from A to B. So this drop in head is in fact energy loss. Therefore, energy loss from A to B will be simply difference of the two heads. So it is 4.44 meters. So this is in terms of head of water. So this is the answer. So in case discharge is also asked, so that is very easy to obtain. We know discharge Q is equal to area into velocity of flow, area of cross section of pipe, and that is nothing but pi by 4 into d square. D is 0.3 meter, it is given to us. So we can easily get it from this formula. Pi by 4 into diameter square into velocity is 24.4 meters per second. So this comes out to be 1.724 meter cube per second. The second example that is taken here is this. A pipe of length 300 meters has a slope of 1 in 100. So here it is horizontal distance and this is vertical distance, and tapers from 1 meter diameter at the higher end to 0.6 meter diameter at the lower end. The discharge of water flowing through this pipe is 5400 liters per minute. If the pressure at the higher end is 68.67 kilopascals, find the pressure at the lower end. Neglect the losses. So in this case, the data are like this. We have a pipe running like this. So water is flowing through this in this direction, and length of the pipe is 300 meters. Slope is in such a way that there is a drop of 1 meter after every 100 meters. So it is one vertical, 100 horizontal slope. The difference in levels of the 2 points, that is higher end, this is higher end, this is lower end of the pipe. The difference in the levels of these 2 points will be equal to this length divided by 100. So h is difference in elevations of, let us say, point 1, and lower point is number 2. So h is L by 100. Now in this particular case, L is approximately equal to 300 because slope 1:100 is a small slope. So we can consider L close to 300, although L will be equal to 300 squared minus h square square root. So according to Pythagoras theorem, we can get L, but since h is very small as compared to 300, so we can take L very close to 300. If we take L as 300, h will be 300 by 100, that is 3 meters. So this is the difference in levels of the 2 points. Now we will calculate the discharge first of all, and we know discharge is given as 5400 liters per minute. In terms of meter cube per second, we can get it like this, divided by 1000 to make it meter cube, and to make minutes to seconds we will divide by 60. So we get it to be 0.09 meter cube per second, which is also called as cubic. Now area of cross section, which is also called as area of flow section at higher end, which is section 1, can be obtained by pi by 4 into diameter at higher end. It is given as 1.2 meters. Square of it comes out with 1.131 meters square. Therefore, velocity at higher end will be v1 is equal to q upon a1. a1 is this area for section at higher end, that is section 1. So q is 0.09, which is this one. Area of projection has just been obtained. So this comes out to be 0.0796 meter per second. So this is the velocity v1. Similarly, a2, which is area of cross section or flow section at lower end, will be equal to pi by 4 into diameter square. Diameter at lower end is 0.6 meters. So this will be 0.6 square. It is 0.2827 meters square. Therefore, velocity v2, that is velocity at cross section number 2 or lower end, will be q by a2. Discharge will remain same. Discharge is not going to change since continuity equation is satisfied. q1 is equal to q2, so that means a1 v1 should be equal to a2 v2. So for keeping discharge same, velocity must change because area is changing. So q by a2 is given by 0.09 by 0.2827. We get it as 0.3184 meter per second. So having obtained velocities, we will now apply Bernoulli's theorem. So now applying Bernoulli's theorem at section 1 and 2. So according to this theorem, we can write v1 by w plus v1 square by 2z plus z1 must be equal to v2 by w plus v2 square by 2z plus z2. And we generally add losses if there are some losses, but in this case there is no loss. It is given that neglect losses. In this case, P1 is given to us, and that is 68.67 kilopascals. That is given to us here, and P2 is required, so we need to determine P2, that is pressure at lower end. P1 is known, V1 is known, Z1 and Z2 are yet to be found. P2 is to be found, V2 is known, W is specific weight of water, which is 9810 newtons per meter cube. So here, if we look at Z1 and Z2, that is the heights of the two ends from datum. So suppose this is the pipe, this is end 1, this is end 2, and say this is the datum, which is horizontal. So this height is Z1 and height of second point above the atom is Z2. So here we can say Z1 minus Z2 will be equal to height difference between the 2 points. So elevation difference between the 2 points is h, which was obtained to be 3 meters earlier. Here is the difference between the two levels of the pipe. Therefore, let us apply this equation now. P1 is 68.67 kilopascal. So if we multiply it with 10 per 3, it becomes Pascal. And Pascal is Newton per meter square. So this is to be used in this equation. So P1 is 68.67 into 10 to the power 3 divided by W plus V1 square. V1 is 0.0796 by 2G plus Z1 is equal to P2. P2 is unknown, divided by W plus V2 divided by 2G plus Z2. Z2 can be brought to the left side. So this will become Z1 minus Z2, that is H, which is 3 meters. So we will have this equation now. If Z2 is brought to the left side, we will get Z1 minus Z2, that is 3 meters here. So after solving this, we must get P2 by 9810 is equal to 9.995. So this much meters is the head of water, which is equivalent to the pressure P2. So this much head of water will create how much pressure? We know that pressure given by 9.995 meters of height will be rho GH. Rho into G is W, which is specific weight into H. H is this height of water column. Same way we get pressure P2 as 9.995 into W, that is 9810. And this comes out to be 98.051 kilonewton per meter square, because this will be in terms of Newton per meter square. So we have to divide it by 1000 to get it. So that can also be written as 98.051 kilopascals. So this is the answer, which is the pressure at lower end. The third example that I have taken is this one. A pump of power 15 kilowatt has 80% efficiency. It is lifting oil of specific gravity 0.85 to an overhead tank as shown in the figure. If the losses in the entire system are 1.75 meter of flowing liquid, so that means it is the head loss, HL. So what we have to determine, it is discharge, find the discharge. Here oil is being lifted up by this pump from this tank to the tank above here. So what we have to do here, it's simple. Apply Bernoulli's equation at this level and at this level. So this is the initial level of oil, this is the final level, the level up to which this oil is being raised or being lifted. This is datum head 1, and this 25 is datum head 2 relative to some datum, which can be anywhere, it is just horizontal floor. And this can be 5 meters and this is 25 meters. Now at level 1, that is at this level, Z1 is 5 meters, pressure is given as 41.7 kilonewton per meter square, velocity is not given because it is very low, so it can be neglected, it can be taken as 0. Now at level 2, Z2 is 25 meters, P2 is equal to atmospheric pressure because the upper tank is open to air, so therefore pressure here will be 0. So all the pressures that we write here in Bernoulli's theorem, they are gauge pressures. That means they are the difference of actual pressure and atmospheric pressure. If P is equal to ATM, so P, that is gauge pressure, becomes 0 if P pressure is atmospheric pressure. So this is 0 in this case. And V2 is also very low because there is a slow rise in liquid here. So it is very low and it can also be neglected. Kinetic heads are 0. Now let us apply Bernoulli's equation here. Applying Bernoulli's equation at the 2 points, we can write P1 by W plus V1 square by 2G plus Z1 will be equal to P2 by W plus V2 square by 2G plus Z2 plus head loss. Now in this case, the main thing is pump is providing some external power to the fluid due to which it is rising, it is being lifted. So this external power is generally expressed in terms of head being produced by pump. So if you see, there is some head which is being added to the oil due to power provided by the pump, and that has to be added here because whatever energy is there at level 1, that has to be supplied some external energy from the pump so that we can have this head at level 2. Now this means energy in terms of head, including losses, because of the pump level is increasing. We know V1, V1, Z1, V2, V2, Z2 and head loss. So head loss is 1.75 meters. It is given in the statement here. The rest of the things are also known. Now here all the data are available. Head loss is 1.75 meters and W, which is specific weight of oil, that can be given by specific gravity of oil into unit weight of water, which is 9810 newtons per meter cube, and specific gravity is given as 0.85 in the statement. So it will be 0.85 into 9810 newtons per meter cube. Now let us put all the values here. P1 is 41.7 kilo Newton per meter square, so we multiply it with 1000 to convert it into Newton per meter square, divided by W, which is 0.85 into 9810 plus V1 square by 2G will become 0, Z1 is 5 plus HM is unknown, which is head provided by the pump. This head is generally known as manometric head, which comes from the pump. P2 is also 0 plus V1 V2 square by 2G again 0 plus Z2 is 25 plus head loss is 1.75. So from this equation we can get HM, that is manometric head of the pump, to be 16.75 meters of oil. So that is as good as height of oil column which is being produced by pump. So essentially pump is lifting oil by 16.75 meters. Now what is the power provided to oil by pump, or you can say it is energy provided by the pump to the oil per second. So that should be weight of oil into height by which this weight is being traveled. So we know work done is equal to force into distance. So this is force and this is distance, and this is weight per second, weight of oil being lifted per second, and into height by which it is lifted. That will give us the work done per second by the pump, and it is power. So weight can be obtained from density, specific weight of oil into volume of oil per unit time into height by which oil is being lifted. So W into volume per unit time is nothing but discharge into HM. So here Q is equal to discharge of oil in the pipe. So that is simply volume flowing per second. Therefore, efficiency of the pump will be eta equal to actual power being generated divided by power of the pump. And we know power is given in the statement as 15 kilowatts. It is given in the question. And eta is also given as 80%, which can be written as 0.8 in fraction, is equal to W. W is 0.85 into 9810 into discharge Q into HM. HM was obtained to be 16.75 meters. It was obtained here. Divided by P. P is 15 kilowatts, so 15,000 watts. So from here, everything is known except Q. Q can be obtained as 0.086 meter cube per second. So that is the answer. If we multiply it with 1000, we get it in liters. It is 6 liters per second. So that is the answer. Thank you for attention.